Hi everyone, welcome back to my channel. This is M.Poornima and you're watching video lecture series on field theory. Come, let's go into the video. So in last video, we have seen introduction about Maxwell's equations and what you're going to cover in this video lecture series. And we have completed Gauss law for electric field intensity. So today we are going to start with Gauss law for magnetic field. Come, today we can start the video. Okay, first of all, Gauss law for magnetic field. What is Gauss law for magnetic field tells? The total magnetic flux crossing the closed surface equal to 0. So the total magnetic flux crossing the closed surface, the total magnetic flux crossing the closed surface, the total magnetic flux crossing the closed surface equal to 0. So in previous, the total magnetic flux crossing the closed surface is equal, the total magnetic flux crossing the closed surface is equal to charge. Here for electric field, in magnetic field, it is 0. Okay, the reason for this is the magnetic flux line are always closed in nature. The magnetic flux line are always closed in nature. Due to the closed surface in the presence of these lines, this will give the same number of incoming and outgoing flux line. What happens here? The incoming flux line and outgoing flux lines are equal. So what happens finally? Its total flux will get 0. The incoming flux is considered as positive and the outgoing flux is considered as negative. So automatically it get cancels and finally we'll get 0 answer. So this is why we are getting 0 for Gauss law magnetic field. Okay. Now coming to magnetic flux line penetrating to be closed surface. Here what happens here is magnetic flux line. You can see here flux. You can see the flux lines comes here. You can see the flux line comes. What happens? So this line and this line. What happens? The magnetic flux line penetrating closed surface. In a closed surface, what happens? It is an magnetic flux density beam. What happens here? The closed surface gets described. Now, here we can see the integral form. We have two form. So integral form. This is your integral form. Magnetic flux. In integral form. In integral form, what we are going to do is in integral form, the closed surface. So in a closed surface, magnetic flux density with respect to area is equal to 0. The magnetic flux density with respect to area, magnetic induction, the Tesla. So we can see what is this. This reminds that there is an integral over a closed surface area. This reminds the integral of a closed surface area. And what S reminds for? So S reminds that is a surface integral. This is a surface integral, not an volume or a line integral. So here we are taking the surface integral. What B represents the magnetic induction in a Tesla. What B represents is magnetic induction in Tesla. Okay, here comes the B. Here what are the reminds the magnetic field in the vectors. So this symbol represents the vector form. This symbol represents the vector form. And what about this? The dot product tells that you have to find the part of B vector parallel to N vector. B vector parallel to N vector. So B vector must be parallel to N vector, that is perpendicular to the surface, which is perpendicular to the surface, perpendicular. So the unit vector normals to the surface. The unit vector normals to the surface. This is what is the N cap. This is a unit vector which is a normal to the surface, and a dA represents the increment of surface area in m square. The increment of this represents the increment of surface area in m square. And this is what an integral form of magnetic flux. Integral form of magnetic flux. Now we can see the differential form. Here we can see the differential form. Okay, here we can see the differential form. So differential form, what is the dot product of magnetic flux. So dot product, what is this? So what this symbol, first we can see what this symbol represents. That is what differential operator called del R nabla. Del or nabla. So this symbol it is called as del or nabla. And what happens? This is a dot product turns that the del operator into the divergence. So this comes as the del operator and the divergence. Del operator in the divergence. And this is the vector product. This is the vector operator. This symbol represents the vector operator. And what about H? H is the magnetic field in area of pyramid. So A by M. So magnetic field. So this reminds that the magnetic field in the vector, magnetic field in a is a vector, magnetic field in a vector form, magnetic field in a vector form, that is finally is equal to 0. In differential form, this finally is equal to 0. So today in this video, we have seen the integral, what is Gauss law for magnetic field and Gauss law for magnetic field, both in the integral form and differential form. In next class, we can come up with some other law. Thank you so much for watching this video.